Okay, so for this first lesson, we are going to review the first 3 chapters of the book, which covers why we do econometrics and basic statistics and probability. Hopefully, everything we talk about is just review of basic statistics you would have learned in previous classes. So, an overview of the goals of this course are to utilize our knowledge of economics and business to identify important relationships. The models we will focus on are quantitative in nature. A lot of the models we will work on are variations of regression, such as simple linear regression or multiple regression. We will find our beta coefficients to determine what the relationship is between our dependent and independent variables. A few examples of the kinds of problems we can address are stated here. The dependent variable is student achievement, and the independent variable is class size, or student-to-teacher ratio. What we want to find is the effect of reducing class size on student achievement. If we use regression, we will find the amount of change for the reduction of one student will increase student achievement by our beta coefficient for our independent variable. But we will talk more about that in the coming weeks. Another interesting question is, what is the effect of the Fed changing interest rates? If you're paying attention to financial news, you will know that interest rates were just dropped back in July and that there might be another interest rate drop at the September Fed meeting, which is in the middle of September. As a financial analyst, you might want to predict the effect on bonds or the stock market in order to take advantage of the change in interest rates to make more money. So in an ideal world, we could set up randomized experiments. However, this is generally hard to control, and most of the time, ethics come into play. So, in general, we have to use observational data, which is non-experimental. This course focuses on the kinds of analysis we can successfully use to cope with the fact that we have to use observational data. It's also a lot easier to get a hold of observational data, especially with the internet now and lots of banks of data sources from the government and other sources. In this course, you will focus on learning models for estimating causal effects using observational data. Something called effect size will be very important. Many people focus on statistical significance, but a result can be significant but have a small effect size, which really adds little or no value to your study. We will mostly focus on a lot of different kinds of regression. One that is important is called panel regression, or longitudinal time series analysis, and is specific to econometrics. The other kinds of regression can be applied to many fields. So I suggest you read Chapter 1 to get an idea of the kind of problems and questions we will look to solve and understand through our analysis this semester. So now let's start reviewing probability and statistics with a sample problem. Our problem is the effect of class size on standardized test scores. We have to use quantitative data to answer this question. The state of California collected data on 420 elementary schools, focusing on 5th graders. Our variables of interest are the student-to-teacher ratio, and the average scores on the Stanford 9 achievement test. Here is a summary of the basic statistics of those two variables. However, we really have no idea about the relationship between those two variables just based on this table. How do they actually relate? We know we can have the average and the percentile and the standard deviation of what this data looks like, but it doesn't really tell us how they relate. If we use a scatter plot, we can start to identify the relationship, but what does the figure actually show? We are going to need to do further analysis to get an idea of the answer to our initial hypothesis. So we're going to look at a few possibilities on how to answer our question of class size on student achievement. Since we cannot have the full population, which would be all possible schools and fifth grade classes in the state of California, or the whole world if we really wanted the full population for how this would affect, we have to use a sample, and thus our results will be an estimate of that population. Second thing we will need to do is a hypothesis test. This will let us know if our results have statistical significance as to whether the two groups are actually different. Finally, we will find a confidence interval. Confidence interval does not quantify the variability of the data. A 95% confidence interval states that 95% of the time, the true mean of the population will be in this interval, contrary to the belief that 95% of the values will fall in this range, which is incorrect. This is a major misconception and misinterpretation of what a confidence interval is. For our first analysis, we're going to break the data into two groups. One that have a student-to-teacher ratio of less than 20, and another group that has 20 or more students per class. So we have the average and the standard deviation in our sample size. We can see that the two samples are of different sizes. First, we find an estimate. We take the difference between our two groups. Since they are of two different size groups, we need to account for that. We normalize the data by dividing by the sample size of each of the groups to average the scores. For this data, we get 7.4. Well, what does that actually mean? Is that significant to warrant a change to the class sizes? I do not know. Let's continue the analysis. Our next test is to set up a hypothesis test. We're going to do a difference in means test, also called a t-test. We calculate the t-statistic by finding the difference between our two groups divided by the standard error times that difference. We calculate the t-statistic for our two groups and obtain a t-statistic of 4.05. We find that our t-statistic is high and thus statistically significant at the 5% level. Thus, we can reject the null hypothesis that the two groups are the same. So now we know that the two groups are different on class size's effect on student achievement. The last step is to calculate our confidence interval. We take the difference of our two groups and add or subtract our significance level, which is 1.96 for the 5% level. And we multiply that by our standard error times the difference of our two groups. Since the range does not include 0, we know that 95% of the time the true population mean is in this range. We are confident at the 95% level that these two groups are not receiving the same effect. Okay, let's continue reviewing statistical theory on the next few slides. A population is the set of all possible values in our example, all the school districts in the state of California. For our population, we will take a random variable or outcome, or sample. Next, we will talk about probability distributions. Probability distribution is a mathematical function that provides the probability of occurrence for a random variable. Probability distributions can be discrete or continuous. An example would be the normal distribution or bell curve. The closer you get to the mean, the value, the higher the probability of occurrence. When we describe a population description, we describe them in moments. The first is the mean, also the expected value, which is the long-term average value if you were to take many random values. From that probability distribution, the next is standard deviation, which tells us the spread of the probability distribution. The third moment is called skewness, which is how off-center the probability distribution is. A normal distribution would have a skewness of 0. Kurtosis is the fatness of the tails and really tells us the likelihood of larger values. If two random variables have a joint distribution, then the covariance between the two variables. Covariance is a measure of the relationship between the two variables. A lot of algorithms that work well with survey data use covariance-based approaches. One such is partial least squares or structural equation modeling. Do not think, though, that it will be a focus in this class. We can calculate the Pearson's correlation coefficient by using the covariance and variance values. This should be easy to remember. If you have a positive correlation, then the linear relationship is positive. If it is a negative correlation, then there is a negative linear relationship. And if it is 0, then there is no linear relationship. On a scatter plot, this is what the different plots would look like for the different kinds of correlation. The first two are obvious. If you have a positive slope, then you have a positive correlation. If you have a negative slope, then you have a negative correlation. If the scatter plot looks completely random, then there is no correlation between the two variables. The last shows a quadratic correlation, which is nonlinear, so we would need to transform the data or use a quadratic function to work with that data. To define conditional in the sense of statistical theory, I want you to focus on the notation. In the middle of the screen, you see E, Y, vertical bar, X equal X. Well, that is read as the expectation of Y given that X equals X. In our example problem a little lower, it would be the expectation of test scores given that the student-to-teacher ratio is less than 20. Basically, what is the average test scores for classes that have less than 20 students in the class? Seems like an overly complicated way to say that, but you have to learn the notation to understand other concepts in this class. The conditional mean is important when we are talking about predictions. Basically, if we have some random variable x, and we know it is really y, then we want to predict y given some value of x. When we use regression next week, we will want to predict some future value, so this will be important. Simple random sampling is where we choose an outcome from a population at random. This is important because we have to use random sampling to eliminate systematic selection bias. We'll learn a lot of the prerequisites to using our regression algorithms require random samples, normal distributed data, etc. But we'll talk about that next week. We have to use estimator because, in general, we cannot have the true value of the population. If you recall, the value mu is the population mean or average. We use y bar as an estimator for that population, as it is the average drawn from our sample. Y1 is the first random sample, followed by Y2, etc., etc. Our estimator y bar is made up of random samples. Each sample is drawn at random, and had a different sample been drawn, we would have gotten a different value. Depending on the sample size, which we use the letter n to represent sample size, The distribution of our sample mean is over different sample sizes is called the sampling distribution. You can look at an example. Let's say we have a Bernoulli random variable, which is a binary variable that can be only 0 or 1. It has a probability distribution of being 0 22% of the time and 1 78% of the time. To find the average or the expectation of y, we take the probability of our first outcome times the probability of our complement, which is 1 minus p. We find the variance by multiplying our probability of one outcome times the complement. However, our interest is the sampling distribution. So what happens when we increase the sampling size? We can see that our expectations change as we continue to draw more samples. If we have 100 samples, we get the sampling distribution in figure D, which shows a bell-shaped distribution about the initial expectation of 1, which was 0.78 or 78%. Why does that occur? The sampling distribution of y bar when n is large is important due to the law of large numbers and the central limit theorem. Basically, as our sample size increases, our sample average y bar will become closer and closer to the actual population mean mu. Hence, why when we do studies, we want as large a sample size as possible. You can also calculate out power to find the exact sample size you need to actually do it. Generally, the more sample size you have, the better results. The second point is that due to the central limit theorem, the difference between our sample mean and the population mean decreases as that decreases, the distribution will look more and more normal. Hypothesis testing can involve one-sided or two-sided tails. Generally, we will want to use a two-sided t-test to test both directions. The two-sided is generally regarded as more appropriate unless you actually know for a fact that your hypothesis goes a direction, which is pretty rare. With the one-tailed test, it is easier to get a significant result and has more power, but most statisticians know this and will think you are skewing your results unless you have a concrete reason of why you chose a one-tailed test. Some important terminology are p-values and significance level. Statistical significance just states how likely a more extreme value is likely to occur. People generally take this too far, though. You can have a statistically significant result, but if there is no actual bearing on the problem, then you'll have no effect size. However, we typically accept significance level of 0.05. The link between significance level and p-value is that before we build our research study, we have to pre-specify our significance level, which is typically 0.05. We calculate our t-statistic, and if it is greater than 1.96, the equivalent t-value for a significance level of 5%, then we can reject the null hypothesis. If the p-value is less than 0.05, then it means the same thing. When reporting, it is generally better to give the actual p-value than to just state the null hypothesis was rejected, or yes or no. So people generally like to see what the actual p-value is. Okay, the last thing I want to talk about is confidence intervals, and that a confidence interval is an interval that 95% of the time will contain the true parameter of mu in repeated samples. Okay, so hopefully this was all review, and we can get into the more interesting stuff starting next week, and we'll start doing more sample problems, and it should be interesting. So have a good week, and I'll see you on Tuesday.